Hi, Mr. Richards here. Today's lesson is on probability of compound events. What is a compound event? Well, this is defined as two or more simple events. Now, the probability of a compound event is the fraction of outcomes in the sample space for which the compound event occurs. Now, a tree diagram can help us in finding the probability of compound events or visualizing compound events. So a tree diagram is a diagram used to show the total number of possible outcomes. And in our first example today, we will be using a tree diagram. A greeting card maker offers 3 birthday greetings in 4 possible colors, as shown below. How many different cards can be made from 3 greeting card choices and 4 color choices? Well, let's make a tree diagram. And in this diagram, we'll have greeting being our first part, followed by color, and then we'll take a look at our sample space when it's all said and done. Now, for our greetings, we have 3 choices. We have the humorous, we have the traditional, and we have the romantic. Now, if you were to pick a humorous card, there are 4 color choices that go with that. You could choose a blue, you could choose a green, you could choose an orange, and you could choose a red. And that's what a tree diagram starts to look like. We have our first part with the greetings here, and then, if you will, little branches coming off the humorous part into the possibilities for the colors. Now, traditional, we're still going to have the same 4 options of blue, green, orange, and red with these, as well as romantic. We're still going to have blue, green, orange, and red as possible colors if a romantic greeting was chosen. And so we can summarize this all into our sample space now. We can say that our first sample space, if you chose a humorous card, you could end up with a blue color. If you chose a humorous card, you can end up with a green. You can go humorous orange, and you can go humorous red. You could go traditional blue, traditional green, traditional orange, and traditional red. You could go romantic blue, romantic green, romantic orange, and romantic red. My favorite when I give cards. Now, how many different outcomes are there? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible cards. can be chosen. Now, in a little bit of a preview of what's to come in this lesson, there will be an easier way of solving this called the fundamental counting principle, where we have 3 greetings, we have 4 colors, and we're going to do something with those numbers to get us to 12. Now, we can also use a list to count outcomes. The student government consists of a president, vice president, and treasurer. The candidates for president are Jackson, Juan, and Megan. The candidates for vice president are Jacques, Carlos. And the candidates for treasurer are Lee, Jacob, and Carl. How many ways are there to choose a president, vice president, and treasurer? Now, this list will take a little bit of time, and being organized is super important here to make sure we list all of the different possibilities. I mean, we don't want to go, okay, let's say Jackson, and then Carlos, and Lee, and then Megan, and Lee, and Carlo. You want to stay organized here. So let's set up some columns here. We'll start with our president column, followed by our vice president. We'll just call it VIP, VP. And then we'll do the treasurer. And I want to save room on the right side just in case we need to make another column here for these lists. Now let's start with Jackson. Jackson for president. Well, if we choose Jackson, he could go with Jacques for VP. And if we go Jackson, Jacques, we could then go with Lee for treasurer. But then we have different possibilities for treasurer. And this is the way I'm going to keep this organized. I'm going to keep listing Jackson and Jacques and go through my possible treasurers first. So I could go Jackson, Jacques, Lee. I could go Jackson, Jacques, Jacob. I could go Jackson, Jacques, and lastly, Carl. And those are my 3 Jackson, Jacques possibilities. Now, I'm not done with Jackson yet. We could go Jackson, let's see, Carlos would be the next vice president. And then we would need to run through the 3 treasurer possibilities here. So Jackson, Carlos, Jacob, and Jackson, Carlos, Carl. And that is it for Jackson. We had Jackson, Jacques, Lee, Jackson, Jacques, Jacob, Jackson, Jacques, Carl. Those are the 3 Jackson, Jacques combinations. And then we have Jackson, then with Carlos, we could go Jackson, Carlos, Lee, Jackson, Carlos, Jacob, Jackson, Carlos, Carl. And that's it now for Jackson. Next, we get to move on to Juan for president. Well, we could select Juan for president, and if we do that, we could still pick Jacques for vice president. And guess what? We have 3 then possibilities for treasurer then. With Lee, we could go Juan, Jacques, Jacob. We could go Juan, Jacques, and Carl. And those are my Juan, Jacques, treasurer combinations. What about Carlos for VP? We could go Juan, Carlos, Lee, Juan, Carlos, Jacob. We could go Juan, Carlos, Carl. And that's it for those, for Juan. And we still have Megan. And so now we'll go Megan. We can do Megan and start back up with Jacques. And now these three treasure combinations, Megan, Jacques, Lee. Slide the screen up here a little bit to give myself some more room. We could do Megan, Jacques, Jacob. We could do Megan, Jacques, and Carl. And those are my three Megan-Jacques combinations. When you combine possibilities with combinations, you get combinations, I guess. Let's see. Now we can do Megan, Carlos, and then Lee. And two more. Megan, Carlos, Jacob. Forgot the C. And then lastly, Megan, Carlos, and Carl, last but not least. And now we have an impressive list of possibilities. And when we count these up, let's split these here just to kind of show how these were organized first. But as we count these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 different ways. With these candidates. Now, again, previewing possibly our fundamental counting principle coming at the end of this lesson, how many candidates for president did we have? 3. How many different candidates for vice president did we have? 2. How many different candidates for treasurer did we have? 3. I wonder if there's some way to put those numbers together to get to 18 ways. Now next, find the probability of compound events. A toy robot moves straight ahead until it hits an obstacle. Then it turns, with equal chances of turning left or right. If the robot makes 3 turns, what is the probability that all 3 will be left turns? Let's use a tree diagram here to help us find this probability. We're going to have 3 turns. Turn 1, turn 2, and turn 3. So it's moving along, moving along, moving along, boom, hits a wall. It's either going to go left or right. Now, let's just stick with our left course to start. We moved along, moved along, moved along, made a left, and then, boom, hit another wall or another obstacle. From there, it has 2 possibilities, either left or right. And then we're moving along, moving along, moving along, moving along, boom, hits another wall. Well, if we went left, left, then from there it could either still go left or right. But also from here we could go left or right. So we could have hit a wall, gone left, then left, then left, gone left, left, right. We could have gone left, right, left, left, right, right. But that's just the possibilities if we went left first. What if we went right? We need to find our total sample space here. Well, if we went right, when we hit a wall the second time, we could still go left or right. And then from there, we could have gone with this one, left or right the third time, and the last one, left or right that time as well. So when we look at our sample space here, we could have gone left, left, left. We could have gone left, left, right, left, right, left, left, right, right. We could have gone right, left, left, right, left, right, 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 left, and lastly, right, right, right. What we want to be on quizzes and tests, right, right, right. Either way, what is the probability now that all three will be left turns? Well, we have this track here, the left, left, left track, which matches our left, left, left here. And that is just 1 out of the 1, 2, 3, 4, 5, 6, 7, 8 outcomes. So our answer here is 1 out of 8 possibilities. Now again, going back to that fundamental counting principle that we've been previewing, we had 2 outcomes the first time, we had 2 outcomes the second time, and 2 outcomes the third. I wonder if there's any way to get to the 8 using those numbers. And now the definition we've all been waiting for, fundamental counting principle. What is it? Well, it uses multiplication of the number of ways each event in an experiment can occur to find the number of possible outcomes in a sample space. Now, if we look at our previous examples here, think about example 1. We had 3 greetings. We had 4 colors. What we can do instead of a tree diagram is to say, all right, I can take my 3 greetings and multiply it by my 4 colors to get the 12 cards. What about example 2? Well, I had 3 president choices, I had 2 VP choices, and we had 3 treasurer choices. Well, if we take 3 times 2 times 3, 3 times 2 is 6, times 3 is 18, and that matches the 18 different ways we could have chosen a ballot. In our last example, example 3, we had turn 1, we had 2 ways left or right. Turn 2, we had 2 ways left or right. And turn 3, we had 2 ways left or right. And so if we take 2 times 2 times 2, we get 8 ways that we could have turned. And the left, left, left just happened to be 1 out of those 8 ways. And so now, can we apply that to find the probability of compound events? Henry rolls a number cube and tosses a coin. What is the probability that he will roll a 3 and toss heads? Well, let's look at our number of outcomes here. If we have a number cube, there's 6 ways. In a traditional number cube, 1, 2, 3, 4, 5, 6. So 6 ways in a number cube. Our coin, well, it's heads or tails. So we have 2 ways. So we're going to have 12 possible outcomes here. Now, in finding the probability, what is the probability of getting a 3? It's 1 out of those 6. What is the probability of getting a heads on the coin? It's 1 out of those 2. And just like I can multiply 6 times 2 to determine the number of outcomes, I can take these two probabilities, the 1/6 for getting a 3 and the 1/2 for getting a heads, and I can multiply these together. Probability of getting a 3 times the probability of getting heads is going to equal the probability of doing 3 and heads. And so 1/2 times the 1/6 results in 1/12. And that is my solution. So using the fundamental counting principle is a simpler way of finding probability, as long as you understand where it's coming from. And if we just go back to that example 3 real quick, where we had the 3 left turns, what was the probability of getting a left turn the first time? 1/2. The probability of getting a left turn the second time? 1/2. And the probability of getting a left turn the third time? Once again, 1/2. And when you multiply those together, you can get 1/8. And so the fundamental counting principle really is a great principle to find the probability of compound events. And that is it for this lesson of the probability of compound events. Good luck.